Y is faster than list. I recently compared the processing speeds of and list and was surprised to discover that runs more than 3 times faster than list. I ran the same test with and dict, and the results were practically identical, and both took around 0.1 to 8 seconds million cycles, while list and dict took roughly 0.4 to 8 seconds million cycles each. Why is this? Do and probably and to immediately pass back a copies of some empty stock literal while their explicitly named counterparts, list, dict, tuple, str, fully go about creating an object, whether or not they actually have elements? I have no idea how these two methods differ, but I'd love to find out. I couldn't find an answer in the docs or on so, and searching for empty brackets turned out to be more problematic than I'd expected. I got my timing results by calling timeit.timeit and timeit.timeit list and timeit.timeit and timeit.timeit dict to compare lists and dictionaries, respectively. I'm running Python 2.7.9. I recently discovered y is if true slower than if one that compares the performance of if true to if one and seems to touch on a similar literal versus global scenario. Perhaps it's worth considering as well.
Because list is a function to convert, say, a string to a list object, while is used to create a list off the bat. Try this, might make more sense to you. While gives you an actual list containing whatever you put in it.
Because and a literal syntax. Python can create bytecode just to create the list or dictionary objects. List and dict are separate objects. Their names need to be resolved, the stack has to be involved to push the arguments, the frame has to be stored to retrieve later, and a call has to be made. That all takes more time. For the empty case, that means you have at the very least a load_name, which has to search through the global namespace as well as the built-ins module, followed by a call_function, which has to preserve the current frame. You can time the name lookup separately with timeit. The time discrepancy, there is probably a dictionary hash collision. Subtract those times from the times for calling those objects, and compare the result against the times for using literals. So having to call the object takes an additional 1.00, 0.31 to 0.30 equals 0.39 seconds per 10 million calls. You can avoid the global lookup cost by aliasing the global names as locals. Using a timeit setup, everything you bind to a name is a local. But you never can overcome that call_function cost.
List requires a global lookup and a function call, but compiles to a single instruction. See.
The answers here are great, to the point, and fully cover this question. I'll drop a further step down from bytecode for those interested. I'm using the most recent repo of Python. Older versions behave similar in this regard, but slight changes might be in place. Here's a breakdown of the execution for each of these: build_list for, and call_function for list. The build_list instruction. You should just view the horror. Terribly convoluted, I know. This is how simple it is. Create a new list with pylist_new. This mainly allocates the memory for a new list object, opag signaling the number of arguments on the stack. Straight to the point. Check that nothing went wrong with if list equals null. Add any arguments, In our case, this isn't executed, located on the stack with pylist_set_item, a macro, dot. No wonder it is fast. It's custom made for creating new lists, nothing else, smiley face. The call_function instruction. Here's the first thing you see when you peek at the code handling call_function. Looks pretty harmless, right? Well, no, unfortunately not. Call_function is not a straightforward guy that will call the function immediately, it can't. Instead, it grabs the object from the stack, grabs all arguments of the stack and then switches based on the type of the object. Is it a pick function_type? Nope, it is list. List isn't of type pick function. Py method type? Nope, see previous. Py function type? Nope, see previous. We are calling the list type. The argument passed into call_function is pylist_type. Python now has to call a generic function to handle any callable objects named _PyObject_fastCall keywords, ea more function calls. This function again makes some checks for certain function types, which I cannot understand why, and then, after creating a dict for quargs if required, goes on to call _PyObject_fastCallDict. _PyObject_fastCallDict finally gets us somewhere. After performing even more checks, it grabs the tp_call slot from the type of the type we've passed in. That is, it grabs type.tp_call. It then proceeds to create a tuple out of the arguments passed in with _pystack_tuple and, finally, a call can finally be made. tp_call, which matches type._call__ takes over and finally creates the list object. It calls the lists __new__, which corresponds to pytype_generic new and allocates memory for it with pytype_generic alloc. This is actually the part where it catches up with pylist_new, finally. All the previous are necessary to handle objects in a generic fashion. In the end, type_call calls list.__init__ and initializes the list with any available arguments. Then we go on a returning back the way we came. Smiley face. Finally, remember the load_name, that's another guy that contributes here. It's easy to see that, when dealing with our input, Python generally has to jump through hoops in order to actually find out the appropriate C function to do the job. It doesn't have the courtesy of immediately calling it because it's dynamic. Someone might mask list, and boy do many people do, and another path must be taken. This is where list loses much. The exploring Python needs to do to find out what the heck it should do. Literal syntax, on the other hand, means exactly one thing: it cannot be changed and always behaves in a predetermined way. Footnote: all function names are subject to change from one release to the other. The point still stands and most likely will stand in any future versions. It's the dynamic lookup that slows things down.
Channel.